From phenomena occurring in the depths of space and time, to the structure and behavior of the tiniest particles that compose everything we see, the scope of nuclear physics is vast. Discoveries in nuclear physics point us to a fundamental understanding of our world. Its science explores the conditions prevailing at the beginning of the universe, as well as the building blocks of the elements around us and of which we're made. At the same time, the technology of nuclear physics improves our quality of life through advances in medicine, materials, and security, and along the way, fuels economic progress. Its story is one of discovery and innovation, occurring while in pursuit of the heart of matter. Along this path of discovery and innovation, nuclear physics has spurred progress in many intersecting disciplines and technologies. The National Academy of Sciences 2010 Decadal Report on Nuclear Physics clearly articulates the science objectives and long-term priorities for America in a field that has grown increasingly international in scope. This report finds that nuclear physics remains a thriving and vibrant field, for while much is now known about how our universe is composed and how matter behaves, even more awaits discovery.
Research in nuclear physics is built around very basic questions. How did the universe come to be? How was all the matter in the universe created? I think the innovations and the technical developments that have come out of it have been tremendous for society, but that wasn't the original reason we started to do this. It's the wonder of it all, trying to understand our world. It's very human, and really spectacular thing about us is that we wonder about our beginnings. Why am I here? Why is the universe here? What does it all mean?
What we're really trying to learn from nuclear physics is where everything came from and what was at the very beginning and how does it all fit together. Going all the way back to the very smallest constituents, all the way up through the creation of light nuclei and heavy nuclei, through the whole chain of the creation of heavier and heavier nuclei in supernova explosions, etc., etc.
Everybody learns in school about protons and neutrons and electrons, but the protons and neutrons themselves inside of the nucleus are made up of other smaller particles called quarks. And so we want to study what the nature of the force that holds these things together is. If you can understand that, then you start to understand more about the world we live in and the entire universe around us.
Quarks and gluons are the constituents that make up protons and neutrons. But if you heat up matter to something like 6 trillion degrees, to 10 to 100,000 times the temperature of the sun, then those protons and neutrons dissolve, they essentially melt. The constituents become free and they can roam around. And that's what a quark-gluon plasma is. It existed long ago in the early universe as a primordial soup. But in the laboratory, we can recreate it by colliding together gold nuclei at very, very high energies.
We thought it would be an ideal gas of quarks and gluons, and we made it here at RIC, and we were fantastically surprised because it's not a gas at all. It actually behaves like a liquid that flows with no resistance whatsoever, almost no resistance, and has other very surprising properties that you wouldn't expect for stuff that's 4 trillion degrees. In fact, it behaves very much like stuff at 10 to the minus 7th degrees. So the hottest and the coldest matter on the planet are actually really similar.
That quark-gluon plasma quickly expands and cools, and so after a very brief time, it freezes into those protons and neutrons and other hadrons, which then stream into our detector. We can then study the phase transition as it transitions from that plasma into protons and neutrons, which then can form into nuclei, which then can form into light nuclei and become everything that we are. So when we study quark-gluon plasma, we really study the beginning of all of this.
Once protons and neutrons are created, what holds them together? What forces are at work that allow them to combine? The study of these forces within the nucleus is called quantum chromodynamics, and one of the areas physicists are trying to learn more about is what governs the behavior of the quarks that make up protons and neutrons, and the gluons that carry the strong force in the nucleus.
One of the very strange things about QCD, about quantum chromodynamics, is it's a theory that we can write down mathematically, which features quarks and gluons. And we know that the gluons have to be there to hold the quarks together, but that's something of a passive role. You're not directly seeing the action of the gluons themselves. And the gluons really like to stick to quarks and make the quarks stick together. And there's no reason to believe that there shouldn't be a whole other set of mesons in which the gluons are active. They're doing something. They're in some sort of excited state. And we call these things hybrid mesons. And a big unsolved problem is, where are they?
There has been some tantalizing evidence that these things exist. The theory predicts that there's a whole spectrum of these particles, but they haven't really been seen before because experiments haven't been mounted to specifically look for them. That's why we're building the GluX experiment in Hall D at Jefferson Lab right now to specifically try to map out the entire spectrum of these particles.
So one aspect is the experimental program, for example, GluX searching for these hybrid mesons. But another is, why is it that despite decades of trying, we've never seen an isolated quark or gluon? We always see them in these packets. You can either take three, form what we call a baryon, or you can take a quark and its antiparticle and form a meson. And yet, no matter how hard we smash them, all we get are more baryons and more mesons. We never get a free quark or a free gluon. So this concept called confinement is a huge unsolved problem in physics. Now, if we do see what we expect to see when GluX begins, then that really informs us that we're doing the right things with the theory. If we don't, it's even more interesting, because that suggests, well, we've got to rethink our ideas about precisely how QCD is working to bind these quarks and gluons into mesons and baryons.
If there are questions to be answered concerning the force that binds quarks into protons and neutrons, there are an equal number of questions surrounding how and under what conditions protons and neutrons combine to form the light and heavy elements we find today.
So after the Big Bang, the light elements that it created come together over 1 billion of years and form the stars. It's in these stars that many of the elements we find in nature are formed. But we still don't understand how the heaviest elements are formed.
So it really comes down to a very basic question. What has made all the stuff that we find on Earth? And why do we find so many of a certain type of element and not so much of another type of element?
The key to really narrowing that down will be in the properties of isotopes, unstable isotopes in particular. Isotopes are a version of an element with a certain number, a defined number of protons that determines their chemical properties, and a varying number of accompanying neutrons that defines their physical properties. Some exist in nature and some do not, and it's those that do not that we're interested in because they are part of the path for the heavy elements that we want to understand.
Well, the protons and the neutrons in the nuclei, they form shells just like the electrons form shells in atoms, and just like electron shells are the foundation of chemistry and determine what chemical reactions can happen, the nuclear shells are the foundation of nuclear physics, and they determine how nuclei react. The number of protons and neutrons that you need to fill a shell, those are called magic numbers. And if you fill the shell, then the nucleus becomes like a noble gas. It doesn't like to react anymore and is less reactive. The magic numbers for stable nuclei, they're known since the 50s. But there are hints now from rare isotope experiments that shell structure changes for exotic unstable nuclei. So this has a big effect on understanding of the origin of the elements, because a lot of the heavy elements are actually decay products of these exotic isotopes. So the reaction paths from the light elements to the heavy elements proceed through these unstable isotopes. And if you have a magic number, then suddenly those nuclei become less reactive, and you get an accumulation of abundance at these places. And when you don't have a magic number, you get only scarce production. And so this shell structure imprints itself basically on the distribution of the elements in nature. And there's no way to understand that without understanding where those magic numbers are.
Nuclear physics as a field or scientific interest has contributed a lot to basic science, but beyond that, nuclear physics is largely responsible for the world that we live in. Nuclear physics has provided new technologies and innovations that have spurred the economy forward.
Innovation is the basis of the economy today. We live in a knowledge economy. Innovation takes new ideas and turns them into products and services. And innovation can only work when you have the materials with which to innovate. And that means you've got to have the results of research, nuclear physics, other fields. And if you have that basic knowledge, then engineers can take it and produce products, and innovators and entrepreneurs can take it and make people's lives better.
Today, nearly 20 million nuclear medicine procedures are carried out each year in the United States to diagnose and treat cancers, cardiovascular disease, and certain neurological disorders. Many of the advancements in nuclear medicine, now a routine part of clinical care and daily treatments, were only made possible due to research investments made during the past 50 years.
Many people that have cancer at some point will have some kind of nuclear medicine scan to look at the extent of disease or determine how to treat it. So it's a lot more common than most people realize. Probably everybody knows someone that's had some sort of nuclear medicine. Cancer is a very heterogeneous disease, and so really what we want to look at is tailored diagnostics and tailored therapies. Different isotopes have different chemistry as well as different decay patterns, so we can make different diagnostic drugs, different therapeutic drugs, depending on the new isotopes. And there are isotopes out there that we haven't even explored yet, and it's places like EFRB which can really give us access to those types of isotopes. And by getting our hands on some and experimenting with them and understanding the basic research, we can continue on, learn how to make them better, and develop these more tailored diagnostic tools.
America has long been a leader in investment in basic research. Our country has recognized the importance of it and the payoff of it. Today, other countries are rapidly increasing their spending on all kinds of research, including basic research. We see this especially in the field of nuclear physics, where the most capable machines in the world today are, for the first time, not in the United States. If America is to compete in this world that we're entering, or that we're finding ourselves in, we're going to have to find a way to have our industrial world, our government, and our universities work together much more closely than they have in the past. America can't hope to be first in everything, but we've got to be competitive in the critical fields such as nuclear physics if we're to have an economy. And without an economy, we're not going to solve the problems that this nation faces.
The field of nuclear science is well worth nurturing for the discoveries that are now close at hand. In the coming decade, greater accomplishments will come at a faster pace as nuclear physicists, computer scientists, and applied mathematicians integrate state-of-the-art supercomputers into the process of discovery. The interpretation of data from new accelerator facilities and the ability to carry out calculations of great complexity will lead to new understandings of symmetry and reaction dynamics, and to new predictions of how matter behaves under extreme conditions. There is much we do not yet know, such as how did visible matter come into being? How many more isotopes have yet to be found or to be created? How can we best use the knowledge and technical progress provided by nuclear physics to benefit society? What we do know is this: scientists in nuclear physics, given the right tools and incentives, will continue to scour the interior of the atom and the vastness of the cosmos until they find answers at the heart of matter.